Welcome, Mechanics of Materials students. In this lecture, we're going to explore the stress, both normal and shear, that is going to exist on a plane oriented at some angle to a given reference angle within a material to which we are applying some known set of normal and shear stresses. Okay, so we're going to load the material with forces. Those forces will be distributed over some area. We're going to assume for now that everything's uniform over any plane, whether it's the external faces or surfaces to which we're applying stress, or some plane oriented at some angle. We're going to assume everything's uniform, but we're going to really focus on the effect of orientation. Which direction are you pointing within the material? How's your plane oriented? And what shear and normal stress are you going to see as a result of which way you're facing? So if we look at a really simple example here, we've got a cylinder and we're applying a normal stress, and then so that's sigma applied. And so if we were just to look at this face, obviously our stress, there's no shear, it's all normal, no problem. And I guess if we could envision the plane that forms the circumferential surface, it would all be shear. Of course, there's no real way to load that because it's a free surface. It is in plane stress. But what if we looked at a plane that is at a tilt here in the middle? So we can use some geometry and we can relate the angle of that plane, and we can resolve that into based on the angle that we have here. We can relate that to an angle versus the surface normal, and of course our normal stress with respect to this plane is of course pointing in the direction of the planar surface normal, and then our shear stress is perpendicular to that or parallel to the plane. So we can use geometry and find that the magnitude of our normal stress and our shear stress on this plane is going to be related to this angle theta that defines the tilt of the plane. So we're going to expand on that a little bit. We've calculated this possibly in the past. Depending on where you are in your study of mechanics of materials, you may have calculated sigma prime and tau prime for a particular planar tilt and a particular geometry of material. You may have found that this plane, the area, I'll call it A prime, is a little bit bigger than the area of this, and that is related by the cosine of this angle theta, or the sine, depending on which reference you take. And then of course our sigma and tau are just a vector resolution of what would be the sigma applied here. We'll call it sigma A app. But we'd like to expand that and not have this idea be so specific to a given geometry where we're having to calculate a particular new area for a plane. We'd like to derive a general relationship between any applied sigma in the x, y, and z direction, any applied shear, tau xy, tau yz, tau xz, and then look at the shear and normal stresses on any particular plane, any orientation, kind of irrespective of the size of the material. So we're gonna want to use a small element of material elements. So we're going to kind of go back to the ideas we explored with state of stress at a point where we're going to use a differential volume element. So let's take a look at a little, not quite differential yet. It's a small element. It's delta x, delta y, delta z. And it's located somewhere in a body to which we've applied some stresses. So we've got our delta y, delta z, delta x volume unit, and we put it in plane stress in the xy plane. And we're interested in the state of stress on this plane here. And we're going to define the reference orientation from which we're going to describe the planar normal orientation theta. So here's our planar normal from our plane of interest down here in red. And we're going to reference it to the original x-axis. See, we've got we put our coordinate system here, x going to the right, y going up. So this dotted line is parallel to the x-axis, so that's x there. So we've defined theta as the angle of the planar surface normal of whatever plane we're interested in with respect to the x-axis. So if we're applying stresses in the x, that'll be a sigma xx. If we're looking at a tilt of that plane, if it's parallel, if this surface normal is if theta is 0 and that surface normal is parallel to the x-axis, then the plane is just there is no tilt. It's our reference orientation. If theta is 0, then, or excuse me, if it's 90 degrees, then basically our x prime would correspond to our y in our original system. So what we've defined is a bit of a coordinate transfer system, transform system, where we're transforming according to this angle theta with respect to the x-axis. And that gets really important. When we define this plane, we define it via its planar normal, not by the orientation a line parallel to the plane. It's by a line perpendicular to it. And you'll find as you go on in your studies, or maybe you've already encountered it, that quite often planes are defined by a vector that is normal to them. So a little non-intuitive, but we're going to be using that planar normal to say, hey, the plane that's tilted at 20 degrees, that means that planar normal is tilted at 20 degrees with respect to the x-axis. So let's take this little body. Now we got kind of a triangular slice, and it's actually got some thickness, you can imagine, going back into the paper, into the board, and its thickness is delta z. Okay, so we can define an area of this plane and that plane and the bottom. Now I'll go erase what I just did because it's making it kind of a busy. I'm going to try to erase what I just did. And while I try to erase, we'll just keep going with our derivation. We've got a little bit of a delay with the computer here, with our Wondershare annotation. Okay, so we're going to take our little triangular volume unit here, and we're going to put it in static equilibrium, like we do for so many of these derivations. And we're going to sum the forces in the x, y, and z direction by doing what we did when we defined stress at a point, and we're going to take the let me give a pause here. Okay, so we're going to take our volume unit, and I'm not showing the delta z component going in and out of the paper here, but we're going to take the volume element and put it in static equilibrium. So we're going to sum the forces. Of course, for equilibrium, remember, we don't sum stresses to put things in static equilibrium, we sum forces. So we're going to take all of our stresses, both our primes and our applieds, non-primes, and then we're going to have to multiply them by the area over which they're acting. So we're going to start with our sigma xx prime, the normal stress that is normal to our new plane of interest. So the component of that is in the x direction is, of course, cosine theta, and then that's acting on an area that is equal to delta L in one direction and delta z in the other. So that's one force, and it's acting in the positive x. Then we've got opposing it, we have the corresponding x component of our shear on our new plane, so our tau xy prime. And so we've got because this is acting at a different angle, to get the x component of tau, we take sine of theta because tau is at 90 degrees to sigma on any plane, and then but it's acting on a plane of the same area, that delta L delta z area. Then we have our applied stress in the x direction. Of course, it's working in the negative x direction, so we've got our minus sign here. and it's acting on a plane that is delta y by delta z, and of course delta z again coming out of the board. And then last but not least, we have tau xy here, also acting in the negative x direction, and it's acting on a face that is delta x in one dimension and delta z in the other. So here's our sum of the forces in the x direction. And we can do the same thing with the y direction. So we can take the y component of sigma xx prime. We can take the y component of tau xy prime, and then we'll both of those are going in the positive y direction. Then we've got tau xy in the negative, and we have sigma yy in the negative y direction, and each multiplied by the size of the faces on which they operate. Okay, so that gives us our second equation of equilibrium. So this is, so far we've just applied principles of statics. The only thing that is different is we've used a stress times an area instead of a given force. Okay, now from here on out, all we're going to do is apply some algebra and a little bit of right angle trig. But we're going to do it intelligently with the aim towards simplifying our expression so that we can isolate an expression for sigma xx prime and sigma tau xy prime. So the normal and shear stress on that plane of interest tilted at an angle theta with respect to the x-axis in terms of the tilt angle and all the applied stresses and nothing else. So we presumably would know the stresses we applied because we applied them, or we could measure them as applied. We know the angle we care about, or we could measure an angle of interest. Then all we have to do is crank through a formula, or we could maybe program that formula in, and for any given set of applied stresses, we could maybe plot out, where for what angles in a material that's loaded, we would have maximum tension, compression, and shear, which are important when we're predicting yield and failure. So let's start through the steps of our math simplification. There's quite a few here. So we're going to start with some right angle trig. We're going to recognize the fact that, hey, I can write delta y over delta L as cosine theta, delta x over delta y as sine theta. So I can go back up here, and the first thing I can do is I can get rid of all of these delta z's because they're present in every term. And if we're setting all of these terms equal to 0, I can just basically divide both sides by delta z and get rid of it. Now I'm going to go back and divide again, divide through by delta y. And I won't get rid of them all, but I'll get rid of them from most expressions. So I'm going to divide this term by delta y, and I just, I get a 1. Down here I divide by delta y, and I get another 1. I divide this by delta y, by delta L. Dividing out by delta L's. So I get a 1 and I get a 1. Now I divide by delta L, and I have a delta y over delta L, which is going to give me cosine theta. So I end up with sigma xx, so that's applied normal stress in the x direction, times cosine theta. And I'm going to do the same thing over here. I'm going to get a delta x over delta y. A delta x over delta L. Wow. Planet algebra. Delta x over delta L, which gives me sine theta. So I can rewrite this whole expression down as this. So see, now what I've done is I've gotten rid of all of those delta x, delta y, delta z, delta L, which were basically constructs to help us imagine a small volume of material in static equilibrium, but really aren't useful when we're talking about applying real stresses to real materials. So we kind of wanted to get rid of those, so that's good. What we did is we related them back to that angle of interest of theta. So now we have our normal stress on our tilted plane times cosine theta minus our shear stress on our tilted plane times sine theta, minus our applied stress, normal stress in the x times cosine theta, minus our shear stress on the x face in the y direction, applied times sine theta equals 0. And we can do the same thing by dividing everything by delta L and using our right angle trig identities, or just right angle trig, definitions. SOHCAHTOA, I think it's called. Sine equals opposite over hypotenuse, etc. Regardless, we get a similar expression for our shear and normal stresses on our tilted plane, tilted at angle theta with respect to the x-axis, and our applied shear and normal stresses. So that's half the battle done. We could, what we have now are a set of parametric equations. So if we knew theta and we knew sigma xx and tau xy, we could, we might be able to do something numerically, but as it turns out, we can use a little bit of additional math trickery to get an actual algebraic explicit expression for our sigma xx and our prime and our tau xy prime. That's right. The subscripts are really important here. So what we're going to do is we're going to take advantage of the fact that we're going to leverage a couple of trig identities. The first one is our very well known cosine squared theta plus sine squared theta equals 1. And then we're going to take advantage of our double angle formulas for sine and cosine. So because we end up needing sine and cosine squared, or we need the product of sine and cosine to leverage those, the first thing we're going to do is we're going to go through and we're going to multiply this whole expression by cosine theta. And we're going to end up getting this. So instead of excuse me, make sure we're picking up the recording here. Instead of having a sigma xx prime cosine theta, we have a sigma xx cosine squared. We've moved a few terms over to the other side in this case, but now we have cosine squared, and then we have the sine cosine product. So we're starting to set up to use the cosine sine equals 1/2 of sine 2 theta. So we're starting to set up to use that double angle formula. We do the same down here, and we multiply this expression by sine theta. So our normal stresses end up getting a sine squared, and our shear stresses end up getting a sine cosine. So, and we get this expression. Then we add the two together. Because the shear stresses have an opposite sign, they go away on that side. So we no longer have a tau prime xy. So now we solely have our normal stress on our tilted plane in terms of our applied shear stress and our applied normal stresses and theta. So right here, this is what we were looking for. This last expression with a little star here, that is our stress transformation, giving us the normal stress on a plane tilted at any angle theta with respect to the x-axis in terms of your applied shear stress in the xy. Your applied, of course, it's going to be xy, yx, they're the same, and we're in plane stress, so there's no z's. And our applied normal stresses, xx and xy. And if we want to get the shear stress on that tilted plane, we can basically follow the same maneuver, except we'll subtract instead of adding these. So we'll take these same two expressions and we'll subtract instead of add. That will cause our normal stress components to go away, and we'll be left with just expressions for shear. And so this is now what we need to solve for the shear stress on any plane tilted at an angle theta, whose normal is tilted at an angle theta with respect to the x-axis in terms of what we applied. So here's a summary that basically says the same thing. I won't read it. But we've we can simplify this again a little bit by using our double angle trig formulas and make the final expression a little bit simpler, and it'll also be the launching pad for some other future expressions that allow us to represent these transformations graphically, and that's known as the Mohr Circle. So the shear stress on our tilted plane in the xy direction, and so this is for a body that is in plane stress in the xy plane, is going to be equal to 1/2 of sine 2 theta, where theta is the angle of tilt of the planar normal, times the difference between your applied stress in the y minus your applied stress in the x, normal stresses, plus your applied shear stress in the reference to the x face in the y direction, times cosine of 2 theta. So everything here is in terms of twice the actual angle of your tilted plane of its surface normal. We use a couple more steps to get an expression for our normal stress on that tilted plane. It's a little bit bigger expression, not too much. We got 3 terms, but the angles being cited are again in terms of 2 theta. Very, very important here to get the signs right. We've derived all of these expressions with regards to a tilt angle for that surface normal being defined as positive in the counterclockwise direction. For those of you who are familiar with unit circles and definition of 0 to pi over 2 going clockwise around the unit circle, that is the generally accepted direction of positive angular increase. So if you think about is theta default positive clockwise or counterclockwise, you can think about a unit circle. So these are what we call our stress transformation equations. So if you want to know the shear and normal stress at a plane whose surface normal is tilted at any angle theta with reference to the x-axis, and you know the applied stresses in the x and y direction and applied shears, there you go. You can calculate it for any plane. So knowing we can calculate it for any plane, what plane do we care the most about? The plane where the stresses are the biggest. Because as designers, we know that maximum stresses are where things tend to happen. Usually things we don't want to have happen unless we're doing metals forming or we're trying to make something break. So we're going to be interested in 2 special angles. One, the angle of maximum shear, and number 2, the angle at which we have a maximum or minimum normal stress. So when we say maximum and minimum normal here, we mean algebraic maximum and minimum. So maximum is the largest absolute value, positive or negative. So not absolute, not just the magnitude, irrespective of sign. Sign matters. So in this case, if we had the maximum stress was 10 megapascals and the minimum stress was -2, maximum is 10, minimum is -2. If they could be both positive, we could have 10 and 5. Maximum would be 10, minimum would be 5. They could both be negative. In that case, say we had two directions that gave us normal stresses of -1 and -10, then our maximum stress would be -1. Our minimum would be -10. So don't take the absolute value, in other words. Shouldn't use the word absolute. Do not take the absolute value. Take whichever one is furthest to the right on the number line as maximum, and vice versa. Okay, so we're talking max-min. We're talking extrema. Let's take the first derivative with respect to theta of our shear and normal stress expressions for that tilted plane and see where they're 0. So here's an expression for the first derivative of our tau prime xy, shear stress on our tilted plane. We're going to set it equal to 0, figure out where is it 0, do a little bit of algebraic wrangling, and we can express a tangent of 2 theta as equaling negative sigma xx minus sigma yy, or we could have said positive sigma yy minus sigma xx divided by twice the applied shear stress. So obviously if we took the inverse tangent of this side and divided by 2, that would give us the angle at which the planar normal is tilted with respect to x-axis, where we expect to find shear stress to be the most. So if we're thinking about things like yield, where a material starts going from the elastic zone to the plastic zone, it's going to happen first at that orientation, because that's where we have the maximum shear. So a little bit more important for failure is going to be where we find the maximum tensile stress. So that's our maximum normal or principal normal. First principal normal is another way we denote it. So let's find another extrema. Let's take the first derivative with respect to theta of our normal stress on our tilted plane. And we get a very similar expression. Do some algebra. Here's the results of our first derivative. We're going to set it equal to 0. And we're going to collect terms, and we're going to find the tan of 2 theta for the direction where we would find maximum or minimum normal stress. Remember, first derivative is 0, just says you have a maximum or a minimum. You're going to get 2 times the applied shear stress divided by the difference in the applied normal stress in the x direction minus the applied normal stress in the y direction. These two are negative reciprocals. So basically, which is why we expressed this with a negative sign out here. So it was really easy to see that, wait a minute, just flip it and take away the negative sign. So there's a real geometrical angular relationship between the plane on the orientation of the plane on which we're going to find a max shear and the orientation of the planes on which we're going to find the largest and smallest algebraic normal stresses, so our maximum tensile and our maximum magnitude of tensile and our maximum magnitude of compression or minimum tension. I should just stick to the max-min algebraic is probably the more correct and consistent way of saying that. When we get to Mohr circles and we start representing these maximum minimum tensile stresses, or excuse me, normal stresses on a number line, literally, it becomes a little bit easier. So I will stick to max-min algebraic as a way of denoting what's considered our principal normal stresses. Okay, so let's look at the angular relationships. We can basically write that reciprocal, that negative reciprocal relationship between shear and normal, and then literally solve this and get a 2 theta relationship with our inverse tangent, and we can say that 2 times the angle of maximum shear equals 2 times the angle of maximum normal plus or minus pi over 2. And so divide through by 2, so we can say whatever angle at which shear is maximized is equal to the angle at which we have a maximum or minimum normal stress plus or minus 45 degrees. So plane of max shear is oriented at 45 degrees from the planes of maximum or minimum normal stress. So this is on the tilted plane. This is for any combination of applied shear and normal stresses. These are the angles at which we're going to find the max-min shear and normals. So let's take a look at, okay, now we know where in terms of tilt angle to find max shear and max normal. What are they? So let's look at what is the shear stress at a plane where we're going to have a max-min normal stress. So let's go back to our expression for shear stress at any angle. So we're backing up to this expression. And we're just going to plug in the angle of interest, basically. So we're doing a lot of flipping here, so bear with me. So we're going to end up substituting into this expression. We have our 2 identified sigmas, and we're going to collect some terms and express all of this in terms of a tangent. So again, we're taking our We're taking an angle that corresponds to maximum normal and then figuring out, what shear stress would apply on that angle. So we factored out a cosine of 2 theta, and so that allowed us to express this first term in terms of a tangent. Okay, so if we substitute in, which angle do we care about? Well, we want the angle where tan 2 theta corresponds to whatever was our maximum normal stress. Oh, that tan 2 theta is equal to this. Okay, so down it goes. So the shear stress on some plane where we know that we're going to have a maximum or minimum normal stress can be expressed like this. We've got this term here multiplied by cosine of 2 theta, and theta is that angle where we've got the maximum or minimum normal. And we notice something kind of interesting. We have 2 times the applied shear stress multiplied by sigma yy minus sigma xx divided by sigma xx minus sigma yy. Well, that's -1. So we end up with negative applied shear stress plus positive applied shear stress times cosine of 2 theta. So now you can see why we factored out the cosine 2 theta, because it doesn't matter. Because if we take the expression for shear on any plane at any angle with respect to the x-axis, use surface normal with respect to the x-axis, and we say, okay, put in an expression for the plane where the normal stress is maximum or minimum, we find that regardless, shear is going to be 0. So that's another important characteristic of what are called the principal planes, or the planes of principal normal stresses. When our normal stress is maximized or minimized, shear goes to 0. This is not true of planes where we have a maximum shear stress. We could still have a tensile stress or a net tensile net compressive stress on a plane of maximum shear. So it only works one way. And again, that'll be really obvious when we start expressing these relationships graphically. Okay. We're going to take a pause, and then we're going to dive into a couple of examples and put these formulas to work. But remember, so far, we've derived them. We're not going to go back to the derivations. So we just want to show where they came from. But remember, you've got 4 important relationships. 1, shear stress on any plane whose surface normal is tilted at some angle theta counterclockwise direction to the x-axis, whatever you've defined the x-axis to be. The normal stress on that same plane oriented at some angle theta going counterclockwise to whatever you've designated as the x-axis. And then the relationships for what angle wherever is shear stress maximized, and at what angle wherever is normal stress maximized and minimized. Now, last question before we break, why didn't we care about maximum or minimum shear? Because we're talking about algebraic, like, on a number line. Remember, maximum and minimum shear they're going to be the same magnitude, but just squishing our angle in basically in a different direction, but would affect the same shear strain. So a tau xy and a tau yx are going to have the same value. They're going to lead to a corresponding difference, an opposite difference at 90 degrees, but they're effectively equivalent. So from a standpoint of material deformation and properties, having a positive negative shear is less consequential than having a compressive or tensile normal stress. So there was that positive negative aspect with shear when we talk about max shear. You can have a positive and negative, and we'll show that in this example, but it is not as consequential as a positive negative normal stress. So we will see that more algebraically in the example, but just wanted to point that out. We're kind of switching back and forth between shear, where really it's the absolute magnitude that matters, so take the absolute value, versus normal, where don't. So We'll see that in the example, so stay tuned.